Now we're going to start to look at the derivative as sort of its own entity and describe it as a function itself. The derivative as a function. So we're not really going to do examples in this video. We're just going to introduce this concept and why it would be useful. So we'll start with, let's recall what f prime at a value a is defined as. We know it's the derivative of the function f at a, but the way to calculate it is the limit as h goes to 0 of f of a plus h minus f of a all over h. And so this can be true for various values of a. So what we can do is we can consider it as a function, by changing a to the variable x, so it looks like our typical f of x notation. So we'll consider it as a function. And so when you think about it that way, it turns into f prime as your function of x, and it's still the limit as h goes to 0, but instead of f of a plus h, you look at f of x plus h, and then minus f of x all over h. And so this is what it would look like as a function. So what does it mean? So what is the output, if you recall? So the output of the f prime function is the slope of f's, that's a bad notation, that looks like f prime again. Let's say is the slope of the tangent line to the function f. So the output of f prime relates back to the original function f. So it's the slope of the tangent line to f at the value of whatever x happens to be. So this function, excuse me, been at a volleyball tournament screaming all day. This function outputs slopes of tangent lines for the f function. That's really key here. So what are the advantages of having this as a function? So the reason that we like this is this allows us to apply function concepts. You know, your standard sort of function concepts. For example, we could graph the f prime function. So maybe given a function f, we could graph its derivative also, where the y values on the derivative function are the slopes of the tangent lines to the f function. Okay, we could find domain. So anything we could do with a function, we could do with the derivative now. The second thing, and maybe the bigger aspect, or the most frequently used aspect, is we can find subsequent derivatives. Okay, so we can do things like look at the derivative of the derivative, and the way we write that is with f and a double prime, like two apostrophes. So this is the second. It's called the second derivative. The second derivative. It's also called f double prime. F double prime. It's the derivative of the derivative. So f double prime represents the slopes of the tangent lines to the f prime function. Okay? And then you could continue ad nauseum. You could look at f triple prime, the third derivative. And so once you get past the third derivative, you typically you typically leave behind the prime notation, and then you start to write it. Maybe the fourth derivative would be f with a superscript of 4 in parentheses, and that means the fourth derivative at x. And so this goes on and on. And so each of these will have different meanings, perhaps, and you will encounter f prime, f double prime, and f triple prime somewhat regularly throughout calculus. Okay, but so these are the advantages of considering the derivative as a function itself. Now let's talk about another notation for derivative, because historically there's a battle in calculus because two prominent mathematicians were sort of discovering calculus at the same time. And you can imagine that they would have different ways of describing things, and more specifically, different notations. So you had Newton and you had Leibniz. Well, the Leibniz notation for derivative is not the prime notation. So the Leibniz notation, let's discuss that. We'll just introduce it here. So you've seen it. We'll do a lot more with it later when we look at what's called implicit differentiation. But Leibniz notation, instead of writing f prime of x, Leibniz used an operator, a notation that says, let's take the f function and take its derivative. So the way you might describe this is, the f of x function is the input to some operator. That means take the derivative. And so the way it's typically written is a d over a dx. And so what that means is, what this d over dx means, it means the derivative with respect to the variable x. And this whole with respect to x part, again, is going to be more clear when we get to implicit differentiation, because eventually you'll have equations that have multiple variables in them, mostly x and y, and you want to take the derivative with respect to x and not with respect to y in certain scenarios. Okay, so this means the derivative with respect to x of this function, which is also the same thing as f prime of x. And you may be wondering, well, why would I want to write it this way? Well, this is nice to know how to show that you're taking a derivative of something, right? So we'll see more of that later. Now, the way we read this is d, the letter d, and then we say dx. We don't typically say d over dx. So d dx. So we have d dx of f of x. So that's one way we could write it in Leibniz notation, but it's not the most concise way. If we think of the f of x function as just being y, we could rewrite this as d dx of y. And if we're going to write it that way, and we've got dx on the bottom, why don't we put the y on the top and write it as dy over dx, which this is pronounced as, or this is said as dy dx. And so this means the derivative of y with respect to the variable x. And so dy dx is often interchangeable with f prime of x. Now, you really could say df dx also, if you want to incorporate the name of the particular function you're working with, because y is generic and applies to f of x, g of x, h of x, any function name. But this is Leibniz notation. If you want to do a second derivative, like f double prime of x, it gets a little more complicated. So it's d squared y dx squared. And the same continues for subsequent derivatives. But it's a good time to introduce Leibniz notation here so that you see this operator, especially taking this operator that says take the derivative of some function. Okay? So that's the derivative of this function. We'll do more with it later on.